So what is harmonic distortion? Harmonic distortion is any measure of deviation from a pure sinusoidal waveform. And if any of you aren't sure, that is one right there, an AC waveform. And here's an example of one that has been distorted. So what are the effects? Well, you have conductors getting overheated due to abnormal skin effect. You have overheating of transformers. Both of those are using higher currents, which are creating nuisance tripping and leads to higher utility bills. So some other effects that you might have are backup generators. So if you're using a standby generator or emergency generator, they're going to end up with some of the same issues, the nuisance tripping, the overheating. As generators are being added to buildings or new designs, you're going to have to derate because of the harmonics that could be there. So instead of sizing a generator to 1.5 times the load, you're going to be sizing it to 2 times the load. Basically, you're going to end up getting with enough harmonics that you could be creating voltage distortions within that utility company, which will then start affecting your neighbor's power and increase your utility costs. So back in the 80s, there was a group of, it's a professional organization known as the Electrical and Electronics Engineers. They got together and put together a document of practices that should be followed to help reduce these harmonic current distortions. Over the years, they made a couple of changes. Most recently, the Ieee 519-214 revision. So in the past, it was more about the building harmonics, the harmonics all over the place. It was kind of vague. Well, Ieee 519-214 has now specified that those recommendations are for the whole building and the point of common coupling. So not a piece of equipment, not an addition. They want to know the whole building at that point of common coupling. And what is the point of common coupling? A good rule of thumb is basically it's where the meter socket is. It's not quite exact for every single building and every situation, but that's a good general idea to keep in mind. How do they determine those limits? Well, the building load size. What's that building being used for? Is it going to be a hospital? Is it going to be a school? Airport? That all determines what those limits are going to be. And then again, it's not for individual locations or pieces of equipment. It's for the whole thing overall. So by reducing the whole building harmonic distortion or current distortions, in turn, we are affecting the utility voltages and reducing their issues and limiting their power quality issues, which can affect the neighbors again. And that's kind of what this whole thing comes down to, is how much are you affecting the utility and the consumer next to you? If not, you could be facing higher utility bills and fines. So instead of actually telling you guys exactly how harmonics or harmonic distortions are created with the nonlinear loads, I was going to use a couple of examples here and just kind of show you what it is we're actually looking at and what we're looking for. So I got up here a 6-pulse drive with no impedance and a 6-pulse drive with 5% DC choke. The two images to your left are if you were to hook up an oscilloscope to the input side of that drive. Now you can see here and here that those aren't the nice, smooth sinusoidal waveform anymore. They're kind of a plucky, high amplitude, peaky waveform. And then if you move to the bar graph to the right of that, that's the actual harmonic distortions and what we're concerned with as far as the current distortions. So I don't know if any of you guys have actually ever heard of harmonic or the 5th order of harmonic or the 7th order of harmonics or anything like that. But that's what we're looking at. So the very first bar on your left there is the fundamental current that's being created. That's the current that we actually want that's being used. All the rest of those are your harmonic distortions. And those things are basically putting current. They're being drawn from the utility, but that's what's creating that skin effect, that overheating. It's just getting dissipated as heat. So if you look at the top one there, you can see we got our fundamental current, which is at 100%. And then at our 5th harmonic, We're 74% of that. In our 7th harmonic, we're at 57% of that fundamental current. And now when you look at, once we add 5% DC choke, we've dropped it significantly. So then, what we're really concerned with is total harmonic current distortion of each one of those units. How do we determine that? Well, if you take the 2nd order all the way to the 50th, you square root that by the sum of those and compare it to the first fundamental current, that's actually how you end up with 97.5% harmonic current distortion. So when you're looking at a drive that should be pulling, let's just say 10 amps, you're actually pulling quite a significant amount more than that, almost double. And then by going to a drive that's a 6 pulse with the 5% DC choke, we've got a significant reduction down to almost 40%, just below 40%. So if we look at that in the real world, with a motor or with an actual motor, as an example here, if that motor was hooked up on a standard starter across the line, 20 horsepower, it's going to be pulling in at 26.7 amps and 38 amps peak. Now, if we go back to that 6 pulse drive up top there with no impedance whatsoever, those plucky high amplitude sine waves, it's actually drawing 70.4 amps on the meter. It's not being used. That's where it's getting dissipated as heat, but pulling that off the meter. And then if we switch down and we change that to the drive with 5% DC choke, a significant reduction you can see there of 42.4 amps. So then when you add that with your variable speeds, you're getting a lot more efficient drive than you were with the one without impedance.